If I may just have a quick show of hands. How many of you, in your heart of hearts, sometimes are inclined to think of a talk title like that as a pipe dream? Good. We feel relaxed and free to be honest. That was about a quarter of the audience. I hope to get that down, 0 would be too much to ask, maybe to an eighth by the end. Let's talk about how we can make C++ evolve in a way that makes it both more powerful, because we want that. We don't want to give up anything. We want to increase the power and control we have, but make using C++ simpler than it is today. And there's a proof that we can do it, because we've already been doing it. This is how to be intentional along that same path and double down and do it even better in the future. So I'm going to talk for most of the talk on the last two things, an update on the lifetime profile for simplifying C++ so that we can detect dangling problems, many common sources of dangling, iterators, pointers, string views in our code, which makes our code simpler because then we don't have to teach and learn many of those common things we have to teach today. And then on metaclasses, which makes authoring classes simpler. But first, before I get into those two, which are the bulk of the talk, but they're the what and the how, let's take a few minutes to talk about the why, because that's much more important than diving into solutions. Probably the most common reaction I get, including a few minutes ago, about simplifying by adding stuff is, so let me get this straight, you want to add stuff to this already huge language to make it simpler. Yep, right, I have a coffee I need to get. But it's not adding things to the language in itself, it's to make C++ coding simpler, easier to teach, learn, debug, maintain. So yes, we can do this if the thing we add to the language does one of three things, and there are others, but here are three main ones. If it makes user code simpler, for instance, range 4, we added to the language, so we made the language a page bigger. But we made a lot of C++ code simpler because they could directly express their intent. If we can remove special cases and sharp edges, if we can even discourage, maybe even deprecate some existing hard features that make working with C++ difficult, then we have simplified C++ by adding something. Now we do want to also take away, we'll get to that. Now let's dig into that first bubble, because there are three major categories of ways that we can add a feature that makes user code simpler. The way you always do this, add something that makes things simpler, is by adding an abstraction of some sort, because that lets programmers express their intent more directly. The first bucket, which I'll call, say, a K or constant factor gain, is when we add something like range 4, think of it as I'm adding a fixed name into the language. In that case, it's 4 with a colon. Sometimes it's actually a word like override, but some specific syntax which you can think of as a name, and then the user can invoke that name as a built-in word of power and express their intent more directly. Their code just got simpler because now you can look at range 4, you look at just that first line, and without looking at the body, you know it's going to traverse visiting each element once in order until an exception is thrown or they get to the end. By construction, that's simpler. The second bucket is if you let users make a name, a word of power. This is why concepts are so powerful, because we are letting the user write a name like sortable, and then use it, and the language helps them by letting you overload on it and do other things like that. And I'll call that an n-fold improvement, because now you've not just given one feature, you've given users the ability to write small features. And the third bucket, which is the most powerful thing you can do in a programming language, and you have to be careful here, because it's easy to give too much power in an undisciplined way. If you need convincing, recall Lisp's deffun 3. And if you don't know what that means, Google it and Sutter. What you want to do in the third bucket is give the user a way to make their own word of power, make their own name that has not just a name, but also encapsulated behavior. It's got a hidden part. And today we have exactly three such things in the entire C++ language. The variable, the function, and the class. Yeah, templates are great, but they're just parameterizations of those three. Exceptions are great, but they're more in category 1. We have user-defined encapsulated abstractions in the variable, the function, the class. Now let's start with class, that's the easy one. The definition for this encapsulated abstraction is I can give it a name, okay, I can give a class a name, and there's an exposed part and a hidden part. What's the exposed part of a class? Yell it out. Public interface. What's the hidden part? Private. And then there's protected, which means public to a smaller audience, so it's in between, we're getting granularity, but there's that separation. Now, you can go and look at inline functions in the class body, member variables, they're visible in the source code, the compiler uses that for optimization, but calling code can't use those, they're hidden. For a function, what is the exposed part? The declaration. What's the hidden part? Function body. Again, even if it's inline, the caller just uses the declaration. For a variable, what is the exposed part? Yes, the answers are getting slower. Type and name, exactly right. And what's the hidden part? The current value. And we have accessors to read and write the current value, but you can easily write a function that uses a variable and never looks at its value at all. For instance, a times 2 function says variable star equals 2. Never reads its value, it just doubles it, so it's an abstraction. Of all the features that are currently in the pipeline in the actual core groups or in the standard or on the way to the standard in the C++ committee today, the only other such feature is the module. It is an encapsulation boundary, and that is what makes it so powerful and so important, because you can talk about the exported and the non-exported or hidden parts of a new user-defined abstraction. And that gives you combinatorial composable power. I'm going to talk about two things. When I talk about lifetime rules to diagnose common cases of dangling, that's in the lower left bucket, because we're removing special cases and sharp edges so we don't have to teach them. That simplifies the language as it's used. And metaclasses are in the lower right because they would be, they're very early, it's still an experiment in progress, but we're about a year or two into it, and if they progress, if it works out, they would be another one of those very few things in the bottom right bucket that let you incant a new word of power that's an encapsulated behavior. And that's very powerful. In fact, it addresses both of those two other bubbles on the left. So pop quiz. I've shown this slide before with the title, Not Your Father's C++. On the left is C++ 98 code. Today is modern C++ 11 code. There are more modern things since this, but I've been showing this slide for about 8 years. To the point where C++ 11 feels like a new language, as Bjarne Stroustrup correctly said. And we've been doing this all over the place. On the left is former standard code that still works, still compiles, but now we have simpler ways. How many of you found the trailing return type syntax jarring the first time you saw it? How many of you still find it jarring? A few, a smaller number. So we learn it. And soon, perhaps we can do the simplification at the bottom. Maybe as soon as one of the next 2 meetings, we already have concepts in the language, and if we have the terse syntax notation, then we can do something like the bottom right. But here's a serious question. Of all of these things we just looked at on this slide and on this slide, which are C++ and which are not C++? They're all C++, but they look very different. All of them are C++-ic, we might say, in the spirit of C++, even though they look different superficially. So when we talk about what is C++, we talk about usually 3 things. 2 things, but I'm going to add a third, because it doesn't get mentioned a lot, but it's very important. The first is, of course, zero overhead abstraction. Don't pay for what you don't use. The other half of that, the second line in that bullet, is important, and often people don't talk about it. When they say zero overhead abstraction, some people say, oh, but your feature costs something if you use it. That's not zero overhead. That's not what zero overhead means. Zero overhead means you don't pay for it if you don't use it. But if you do use it, it's going to cost you something. You're opting into it. But it's going to be as efficient as you could reasonably write by hand. It's going to cost something, but it's going to be as efficient as you could reasonably write by hand. That's a zero overhead abstraction. We also like determinism and control, and this comes in various flavors, but I think the right way to summarize it is determinism and control, control over time and space, bounded execution time, space layout, knowing where your data lives. This includes leaving no room for a lower language than C++ other than assembler. It means trust the programmer. All that fits in this bucket. And then we have great link compatibility, so we can use old C++ and new C++ in the same project and link it together, and it works. A historical strength that has let us achieve the zero overhead principle and determinism is that so much in C++ has emphasized static behavior, static typing, static compilation, usually static linking in the standard. And one of the major current trends is if you look at concepts, const, expr, and so many of these other things we're doing, most of them are static or enabling us to do things in a static way that we used to do in a dynamic way. I'll tell you right now, as soon as we get static compile time reflection, I will be leading the charge to remove type ID from the language because there ain't no reason we need it, and we currently pay for what we don't use with type ID all the time. And the moment we do that, our executables will get smaller by removing a feature almost nobody uses, but replacing that dynamic feature, which is one reason they don't use it, with a static feature. So that's the core, I would say, of C++. But let's use the bottom half of the slide to talk about non-core things. So this is not core, but it's very useful pragmatically. Backward source compatibility. Now, when it's backward source compat with C, it's pretty much read-only. The idea is we can easily inhale a C header so we can call the function. So it's about using existing libraries. It's not about writing new code. Remember, Bjarne Stroustrup has been telling people since he started this project, C with classes in 1979, it's C, yes, that compiles. With classes, use those instead, right? So backward source compatibility isn't so you can write code that old way forever. It's so you have a new way to write it, but the backward source compatibility is there when you need it, specifically to call existing libraries. And that's true also for existing C++ code. We have a great backward compatibility story. So what is not core to C++? Well, we already mentioned specific syntax. We're adding new syntaxes all the time. As soon as Bjarne added classes, it was a different language from C, but we liked it, and the class has fueled a generation of languages. It's very powerful. Tedium is not core to C++, no matter how many people believe otherwise. We can have range 4 and override, and you know what? They don't cost anything. Almost all major modern language features can be designed with zero overhead. Like always on garbage collection, no. Always on metadata, no. Opt-in garbage collection, sure. Opt-in metadata, static reflection, and then you save the ones you want and only those, totally zero overhead. So this idea of having a nice language and having zero overhead is not in tension nearly all of the time, and we're improving C++ in exactly that way. And getting good defaults, removing sharp edges like dangling, and maybe your code works, maybe it'll fall over, that's not core to C++. If we can solve that with zero overhead, then we have a better language that is still C++. So as people propose new language features or library features for C++ evolution, but especially language features, I would ask you to please consider questions like these. How does this feature let the programmer express their intent more directly? If you can answer that, you almost certainly have an abstraction, and a good general one. And then we can tweak about how general and how good and how to make it useful. How does this simplify C++ code, C++ as she is spoke, so to say, to read, write, debug, and maintain the code? How does it remove gotchas or special cases or sharp edges, foot guns from the language? And that simplifies the language because we don't have to teach them anymore then, or have them drain our mental overhead as we're using the language. Here's an interesting one. How does this feature remove a place where C++ today does not meet the zero overhead principle with its own features, or determinism principle? There are two such features. Exception handling and RTTI are not zero overhead. Newsflash, they're the ones that are commonly turned off. They are the only two standard C++ features that every major compiler has a way to turn off. That tells you people are voting with their feet. But the reason is because they're not zero overhead and not deterministic. If we solve that, which for example we are in fact already doing for RTTI, for the type ID part, with static reflection, because once you got that you don't need type ID anymore, you can just statically reflect at compile time and just save the stuff, only the stuff you need in your binary. Totally zero overhead. So how does this proposal help fix an outstanding problem like that, which makes C++ even more C++-like than it already is? How can this feature help us remove something someday, to potentially even deprecate, or at least write guidelines and linter tools that say don't do that and give you errors in clean new code, like macros? An example, and I could give many examples where we've done this, but a using alias is a good one. Instead of templatizing typedef, which I initially proposed because we needed that, and I didn't think the committee had appetite for more than that, imagine how surprised I was when the response to that paper was at the next meeting, paper saying, no, let's have a using alias that is left to right and clean like we would want it, and templatize that, and just leave typedef alone for when you need it, for existing code. I was pleasantly surprised to see the committee have appetite for that. And today we are in a world where we can teach people, and the core guidelines say this, don't use typedef in new code. Use a using alias. It can do everything a typedef can do and more, but typedef is still here in this bucket. Now we can have a separate bucket for compatibility mode. And think of it that way. Our modern language and compatibility mode. And the more we add superseding features on this side, the more we can move cruft into compatibility mode. And there's a lot of good we can retain here. But we end up with a simpler language to teach and learn. So please think of this explicitly. We've already been doing it. But let's start viewing backward source compatibility as a zero overhead feature, in the sense of today we pay for it in the language and the standard because we have perfect backward source compat, and we pay for it in complexity of the spec whether we need it or not, and not everybody needs it all the time. So let's look for ways to keep doing what we're already doing and to make new code use the shiny new things and distinguish between the latest, the current modern C++, which is simpler already, and compatibility mode. And if we think of this compatibility mode separately, that will help us to think about how C++ is already evolving. So with that context, let's talk about the first of the two main topics, which is the lifetime extensions for simplifying dangling problems. So the goal here is that to validate the approach that I presented here 3 years ago, and the approach you're going to see today, and that you see in the paper that was posted last week on the core guidelines repo, is still the same model. The main change that we've done, besides a few minor tweaks, is to shift emphasis from whole program guarantees, perfection, to diagnosing common cases, the 80–90% value. And we're going to see examples of that. Now we actually have two implementations. The last time I was on this stage, we had a very early rough prototype that wasn't shippable in Visual C++, and since then we've gradually shipped more of it. Today we have two partial implementations in progress, one based on Clang and one in Visual C++. So thank you to Neil and to Kyle, who aren't here today, but Neil was on stage with me 3 years ago, and Kyle did a lot of the redoing of that analysis. And thank you also to Matthias and Gabor, who we'll see on stage here in just a moment, for their Clang implementation. One of the goals of this analysis is I would like to see if we could make it efficient enough to run during regular compilation, during regular IDE use. And I believe we validated that. This year we can say, yes, that's been validated. The Visual C++ implementation runs in the IDE in a static analysis framework extension. And it runs with real-time squiggles. The performance is sufficient for real-time squiggling of dangling errors in your code. We'll see a couple of example screenshots. And then the Clang implementation is totally unoptimized because these folks have been working on getting the features in. Totally unoptimized, but currently when building reasonably large LLVM translation units, it's about 5% compilation overhead. So these are rules which we can be confident are efficient enough because they run locally. There's no whole program analysis. There's no data flow analysis, only control flow analysis that we can run regularly. And this is important because as soon as you can say all major compilers have warning X, you can stop teaching X, because when you write coding guidelines, when you write books like Scott and I and others have done, you don't need to write items or guidelines about things that all compilers warn on. Today, dangling is not one of those things, so we have to have whole items in books on these problems. If we can detect those reliably during compilation and just expect compilers to do that a few years from now, we can stop teaching quite a bit of what we teach now. So let's see an overview of the approach and then some examples. The idea is we're going to look at local flow control paths. We're going to enforce it statically. So again, this is totally compile time. This is not a sanitizer. It has zero runtime overhead, zero impact on your binary image. The idea is, look, there's basically three kinds of types in the world. There's just plain old types that sit there, values. Then like a point, int x, y. Then there are pointers with a capital P that refer to somebody else's storage but do not own it. That's a raw pointer or a reference. It's a string view. It's a span. It's an iterator. It's a range. It's a filter view from the ranges TS. They're all just that thing. And we don't worry about the details of all those types. We just say there are pointers. They point to something they don't own. And the third category is owners. They somehow store something they do own. That's string, vector, smart pointers, any owning containers that you have. And once we have that, we can have a single set of rules that knows only about values, pointers, and owners. It's the only kinds of types it knows about, and can know when things get invalidated. Here's a simple example. By the way, here's the next 4 slides side by side. I'm going to show them to you just to show these are basically all the same example. Here's a simple one with an int star we set to null. So what we're going to do is we're going to record statically at any given point in the source code as we analyze each function by itself in isolation. What does this local pointer point to? In this case, p when declared points to null. So we say its p set, its points to set is null. That's what it points to. Then we open a scope, we declare an int x, there's a value, that's that third category of type. Then we take the address of x. The result of the address of x expression is a raw pointer, which is a capital P pointer. And its points to set is x. I just took the address of x, so it points to x. When I copy the pointer and I put it into P, I just copy its points to set. So now P points to x, that's its points to set. And now I can say cout star P, and that's fine. When you do the star P, I know that, what is P's P set? Points to X. That's still in scope. Wonderful. I won't give you an error. Star P is fine. But now close that brace and repeat that exact same expression, cout star P, from line B where it's green to line D where it's red. And what happened at that close brace, line C? X was destroyed. So the rule is when a variable goes out of scope, when a variable is destroyed, in any p sets there are, all the p sets you've got going locally, anytime x is mentioned in one of those p sets, replace it with invalid. So in this case, we change the p set of p to invalid. And now when we try to dereference p, we get an error because p set p contains invalid. And we can even say exactly which line invalidated it and what it was pointing to at the time. And if a pointer can point to more than one thing, the p set can have more than one entry. And so you can get false positives because it's going to be conservative, but it shows you when a pointer could have been invalidated, which usually is a bug in your code. Now this is a simple example. We can generalize this, as I mentioned, to user-defined pointer types. And we recognize a lot of them out of the box. For example, anything that looks like an iterator or satisfies the ranges TS range requirements is just auto-detected as a pointer type. You don't have to annotate it. There is an annotation, but you don't need to use it very often. And if you do, you write your own type that has a different interface. You can say, I am a pointer, and then that unlocks all this analysis for users of your type. But a string view, we do that by default. And you can see the Godbolt example live there if you'd like to run it. Please not now, but it's available afterwards. So the string view S, when we default construct it, we say, okay, a default constructed pointer by default is null, points to null. Then I enter a scope, I have a character array, I say S equals A, so I've got now a string view to that array. So P set S is A, string view points to array A, and I can use the string view S sub 0, but at line C, when A is destroyed, I go and I replace A in all P sets with invalid. So now P points to, or S, the string view S, points to invalid. And now when I try to use it on the last line, I get an error. It's the same expression as it was earlier in the function on line B, but it was valid on line B, and it's not valid on line D. And again, there's no data flow analysis. We're not tracking values of anything. All we're doing is following the control flow paths through the function. It's a single pass algorithm, very efficient, and we can compute these answers. So just as we generalized to pointers, let's generalize to owner types. Same example now, but this time with a string. A string is an owner. It owns some data, in this case a character array. Now when I say S equals name on line A, we set the points to set of S to name prime. So if you get a pointer to an owner's storage, it's to owner prime. That's just our convention for it. You're not pointing to owner, which you could also do, but in this case, you're pointing to the thing owned by owner. And now there's another rule. Now you invalidate owner prime, not just if owner is destroyed, but also if it is used in a non-const way, if it is modified. And there are a few cases where you need to annotate, yeah, this non-const use is actually not invalidating, and you can do that. But most of the time, that works great, including that if I say name equals frobos, so I'm assigning to string, I say, any P set that has name prime, because I modified the owner, set it to invalid, because modifying the owner could, and in this case may well have, moved the memory. And then I can diagnose that that string view is dangling on line D, but not on line B. And you can do this in general. Here's a completely different set that when one of the implementers first looked at this, they said, oh no, really? C++ does this? So some of you have known about this for a lot longer. Vector bool, what does its operator subscript return? A proxy, not a bool ref, because it can't, because it's supposed to cram them into bits. That proxy can dangle, and if you use auto proxy equals VB sub 0, your code will work but could dangle if you reassign or if you invalidate the vector by pushback, reserve, such as on line C, and we can detect that just fine, exactly the same rules as before. Finally, function calls. Since we're analyzing each function in isolation, when you call a function, we just assume that any pointers that you get out of it are derived from its inputs. I mean, that's what functions almost always do, is they return stuff that you gave them. And if it's a pointer, we assume that it could be a copy of that pointer that you gave it. If it's an owner, we assume it could be owner prime, derived from owner that you gave it. This can be totally heuristic because you can override this with annotation. The whole point of this heuristic is to make annotation not needed most of the time. The heuristic is that, hey, you know what? If you have a const reference parameter, that combined to R values. People keep forgetting that. So by default, we're going to assume that any pointer you get back didn't come from a const reference owner parameter, unless that's all you got. If that's all you got, okay, you probably got it from that. Turns out this finds bugs. When the implementation returned a pointer derived from its constref parameter and wasn't thinking about, oh, that could be a temporary, or when the caller was doing it and didn't realize what was going on. So let's take a look at some examples. And I have this cute little video that is showing 3 phases of dangling. And I want you to see these 3 phases. The first is, notice he's dangling, but everything's okay so far. There is the dereference. And there's the third state. Did you see the undefined behavior? Dangling, dereference, and then sometime later, undefined behavior. Can we say it all together if you'll humor me? So it's 3 phases: dangling, dereference, undefined behavior. Thank you. And That's actually pretty much what happens. Sometime later, that's what you get. Please welcome to the stage Matthias Guerra and Gabor Horvath, who are the implementers of the Clang-based implementation, and we'll look through some examples together. So thank you very much. First, thank you for doing the hard work to implement this. I know you've come a long way from Europe as well, so thank you for being at CppCon. And by the way, these gentlemen will have a talk later today on implementing this lifetime profile we're talking about in this section of this talk in Clang. So you can find them there to ask questions and see a presentation about more details of the Clang-specific implementation. But now here's an example which I'm going to use screenshots because conference Wi-Fi and because it's more convenient. So here's a screenshot from the Visual C++ implementation, but it's one I know that resonates with you, Matthias. What's going on here with this min example?
Sure. So we start with declaring two variables, x and y. They reduce to int, even though they are auto. And then we use good old std_min to find the minimum of both. And we take actually a reference as a return. So good will point to y, obviously, and then we can print good and everything will be okay. But turns out sometimes later someone comes and say, oh, that's not actually the business logic anymore. I don't want to have the minimum at x and y, I need y plus 1. So we just add 1. What can happen? It's minimum, huh? And it turns out that now bad still binds to the second argument because y plus 1 turns out to be smaller, but y plus 1 is a temporary. So bad will initially bind to y plus 1, but the temporary will be destroyed at end of full expression, so at end of line 14. And now if we do the dereference, things will happen like we just saw.
And so this actually uses those default function call rules I just said. Turns out std_min needed no annotation because it takes two references. People always forget it's reference, not value, which is efficient, except when you dangle. It takes two references and returns a reference. Well, references are just pointers. By default, we assume that the pointer that's returned is derived from the inputs, which is two pointers, so we assume it's one of those. So the points to set you get back is, for bad, is going to be the points to set of x, comma, temp, where temp is y plus 1, and then when temp is destroyed, boom. Does your Clang implementation handle this?
Exactly.
Well, let's take a look. So here's the Clang implementation on Godbolt in the cppxgodbolt.org. And you can find links to these examples in the lifetime paper. There's over 30 links, and here's just a few of them. And so here we see exactly the same thing. And I like how you've got two messages here.
Yes, you will get the warning on the reference in line 12. The squiggles, bad. And it says, oh, dereferencing a dangling pointer, which here's a reference. It's a generalized pointer. And it also gives a node to find out where this reference started dangling. And that's at the end of line 11. You see a squiggle under the semicolon. And the node says, yes, temporary was destroyed here.
Great. Now, Gabor, you had mentioned to me that you were sitting in one of Jason Turner's talks. Is Jason Turner here? Yell if you're here. There's Jason. Thank you for providing us examples. So we all can do this. Here's an example from Jason's talk that you had mentioned. And so we put it into the compiler. What's going on here, and what do we diagnose?
Right, so here we have a local variable, and we will return a reference wrapper, which refers to this local variable. And of course, after the function is returned, the local variable is no longer available, so this reference wrapper will dangle. And as Jason pointed out, what is really interesting about this example, if we use row pointers or references, the compiler would issue a warning for that. But if we use a reference wrapper, none of the major compiler warns. And the reason is that the compilers does not know what the reference wrapper actually is. But if we would show the interface of this class to a developer, then she could infer that it's something like a pointer, that is its type role. And this is exactly what this analysis does. It can infer that this is likely to be something that acts as a pointer. So this helps us detecting this issue.
So this particular one, we never tested reference wrapper, but because it matches the pointer heuristics, we didn't require annotation, and it just recognized it out of the box and happened to get it. So thank you. Now here's another one that was also in Jason's talk, but it was also in an article in a standards paper this summer at our last standards meeting by Nico Iossoutis and Richard Smith of Google. And so everybody comes across this kind of example. So we've had it in a talk, in a paper. What's going on here?
Yes, so maybe you heard a lot of puns about how string view makes the language more unsafe. So what is happening here? We have a string literal that we are converting into a stud string. And during this conversion, we will create a temporary. And stud string will convert into string view because there is an implicit conversion. And this string view will refer to this temporary, which will be gone by the end of the full expression. So in the next line, the string view will dangle. So even though this behavior is kind of dangerous in this language, but if we have the right tools, it will not cause any headache.
Yes. So interestingly, do you notice the error is on line 7, not on line 6? So remember our animation, it wasn't just a gratuitous animation to see somebody smack their head. Like there actually was a teaching value there, because dangling is one thing, it's dereferencing it's where you hit your head, and then sometime after that, you'll get the actual bug manifest as undefined behaviors. The swing comes back and conks you. Line 6 is perfectly fine. In fact, we want to be able to write dangling pointers as long as we don't dereference them, because you do that every time you reuse a pointer variable in a loop. And you set it on the next trip through the loop to something else, and then you use it, and then it dangles. But that's okay, you don't use it till your next trip through the loop, and you want to reuse variables like that. I actually don't like the choice certain other languages have made that diagnose as soon as you invalidate, because invalidating a pointer is not a bug, and it prohibits reusing variables. It's dereferencing or using an invalidated pointer that's a bug. So I really like that the error is on line 7, not on line 6. But now this next example, Matthias, this example, first of all, thank you to the 30 people who replied to the SCM challenge puzzle where I asked you to come up with examples. We're going to have 3 winners in a moment. A quarter of you gave variants of this example. Most of those said vector erase. How bad is this bug, and what's going on here?
So let's first look at what's going on. We have a vector declared in F filled with some elements. We do an iteration over the vector. And when we find an interesting element, say 2, we say, oh, that shouldn't be here. So we erase it. But of course, that makes our vector change size. And so if we don't update our iterator or do something to I, then I will not be what we expect it to be. In the case we see on the screen, we will not even find that in testing, because I will just point to the next element. We will skip one, which we didn't intend, but it will kind of run fine. But then in production, we might actually remove the last element. And then by skipping and incrementing the iterator on the next iteration, we will actually skip past the end. And then we will start looping over uninitialized memory. So this is an error in all cases. And the analysis finds this because it has a notion of where I points to. I points into V. And when we call a non-const function on V, which is erase, then all iterators that point into V get invalidated, because you should get a new one.
So one very interesting thing about this example. There's 2 lines mentioned, 6 and 8. Which one is the error?
So the error happens on line 6, where the warning is, because there we do increment some iterator. But the dangling happens on line 8. And that seems to be wrong order, because usually you first dangle and then you deref. But because the loop, I mean, that's the order how we observe it. In one iteration, where you see the 2, you erase, and then in the next iteration, when incrementing the iterator, then you do some operation to an iterator which is dangling. And that's why you see, logically, the dangling happen after the dereference.
And if you look in the paper, you'll see how this is described. Basically, we take a 1 pass through the function. If there is an if-else, those are basically just divergent and then fork and join control flows in the control flow graph. For a loop, we treat it just like an if-else, except we do it twice, once for the first iteration and once for every non-first iteration. Only once, so not n, just 2 iterations. The first, and then one to all the others. to catch any invalidations in the body of the loop, which would affect subsequent iterations. So a first and a non-first. And now we teach people to write it the bottom way. You have this as an interview question, don't you?
Yes, and it works pretty well. So for reference, you can see on the lower part how you can do it to avoid dangling. And that will also work in the checker. So it will make the checker happy and the interviewer, because we will use the iterator that's returned from erase. And even though erase itself invalidated the vector, we know that the function will return something valid. I mean, we don't assume that functions return invalid state. We will check that in the function body, but here we will assume it at call side, and that's also the correct thing to do. So the fresh iterator we get out of erase will be perfectly valid.
And in fact, one reason you have this as an interview question is because Scott Myers has basically an item on this in effective STL, so it tests whether people read the book and know that. So sad news is that now we don't need that item anymore. If every major compiler gave this warning, because you would just warn it all the time. You might need just a very shorter item saying, when you get this warning, write this pattern. But you wouldn't need to explain the whole thing or how to watch out for it. But now let's talk about null. And Gabor, you had some examples that interested you. What's going on in F1?
Right. So if we look at the first function, the interface doesn't tell us a lot. For example, we cannot know whether P might be null or not. So in this case, we assume that this value might be null. If that's not the case, maybe it is better to use references or some kind of annotation.
And I like your note on line 1 saying, here are the things that you could write this as to silence the warning,
right,
which actually improve the code.
Right. If we look at the second function, we will see if we insert a null check in the function, we will no longer warn for the potential null dereference. This not only makes the code safer, but also clearer, because this way we can see that the user expects P to be null in some cases. And if we look at the third example, you can see that we do not constrain you how to write this null check, because in both of the cases we have two branches. On one branch, the pointer is null. On the other, it is not null. So it's that easy. And if we look at the next function, it's a bit trickier. We still detect that there is an assert, which is basically a precondition check in the current C++. So we will recognize that, and we will not warn on the next line. There is a caveat to this, because if you are compiling your code in a release mode, the assert might disappear because it is a macro. And
it doesn't just disappear from their code, it disappears from the control flow graph that Clang gives you, so you can't see it anymore.
Exactly. So unfortunately, in release builds, you might see a warning there. Fortunately, in the upcoming standard, we will hopefully have a solution to that with the contracts.
Yes, which were just voted in June, just 3-4 months ago in Rapperswil. So we're very glad to have that. And then you can write line 17 as learn to love square brackets, attribute assert colon P, or write it as an expects precondition on F4. But now, what about function F5?
You're right. In function F5, we have a null check, but the null check is not correct. Even if P is not null, but Q is null, we can still, so if P is null and Q is not null, we can still dereference a null pointer, and this check will see this. And in order to fix this error, we need to check the guarding condition. We need to fix the guarding condition.
And finally, what about this pointer chasing node function on line 33?
Yes, in the last function, we can see that when we have a loop, basically we have branches, and we can handle this in a very similar way. So after the loop, we either exited the loop or didn't take it in the first place. And in both cases, the n must be null, so we will be able to find the null dereference.
And this is actually a hard, a known, difficult problem in static analysis theory. And one of the reasons is because if you do data flow analysis, you do something more than local control flow analysis, then you have to start dealing with this loop, and who knows how far it goes because it's dynamic. You can only do so much statically. There is no data flow analysis going on here. We're simply saying, look, there's a fork in the control flow graph and then a join, and along one of those, it's going to be null, or it can still be null. In this case, it's going to be null, so thank you. Now, the last three examples are taken from that Rapperswil paper by Josutis and Smith on all the evils of dangling. And incidentally, this lifetime profile catches all those errors. All or almost all are caught by the Clang implementation today that were in that Rapperswil paper. And here's another one from there. This is the Visual C++ screenshot, just so we show that implementation as well. What's going on here, Matthias?
So we have a function, find or default, which probably many of us have written in one or another way and had to wish that it wasn't a standard. And it takes a map and a key, looks up the key in the map, and if the key is not there, it returns the default value that we have a last parameter. And because we don't intend to mutate the map or the key or the default value, everything can be const, and we of course put references because we don't want to have copies. So that's how we went to our design. And then we call it. So we have our example function, we declare map, it's empty, so we will not find the key at all. We have a key, which is obviously not in the map, and then we call find or default. And as a default value, we give some string literal none. So we hope that s at the end will point to none. But what actually happens is, like in the previous example, none will be constructing a temporary string, and that will go into the function, and the function will return the temporary string, so s will bind to the temporary that contains none. But then the temporary will be destroyed at end of expression, and we have a dangling string. So what we do here is, we don't actually need to know how the implementation of find or default works, because that would need like interprogram analysis, and we don't do that. We just look at the argument types and return types and have a heuristic that tells us what will the return type probably point at. And what our heuristic tells us in this case, that the return thing, so what s binds to, is key or def value. It's one of those, because I have matching types. And when we now do the analysis locally in the call, we see s will either point to key, which is a local variable, or to this temporary that was passed, that got constructed from none. And because it is one of those, and the temporary leaves scope, s gets invalidated, and then we will see the error when we dereference it.
Excellent, thank you. For time, we'll skip over the next couple of examples. You'll find many more in the paper, but we also want to acknowledge 3 examples that were submitted in the SCM challenge. So these 3 folks, if you're in the room, can you please stand up? Can we see you, and can you come to the front? Hayun Ezra Chung, Stefan Guy, and Isabella Muerte. Who's here? All right, run, it's such a long room. Give them a hand. Hello. Hayun? Yes. Thank you for this example. Here is the summary where we're calling a function, and even though we're going through all sorts of callback forwarding interfaces with references and generic lambdas, the analysis is simple. It sees through all that and points out that we're in the line 12, we're getting a pointer to a temporary back, and gives a nice answer. So thank you very much for that. Our second answer was Stefan. Is it Guy or Guy? Guy, I was right the first time, thank you. And this is from Titus Winter's talk, so thank you for giving an example from another talk earlier at the same conference this week. Again, showing, in this case, a directory name that takes a string view, returns a string view. We see through all that, we see the temporary, and diagnose the dangling. And then Isabella, this was a classic and very famous example, a variation of it. So that made it a unique one, so I enjoyed that, thank you. Which is actually tweeted by John Regehr recently, and also discussed by Brian Kernahan. And again, notice that you could think in lines 13 through 15, hey, this is just returning a pointer to a local. Yes, except that current implementations don't see it that way. This analysis does, and we get a nice error. So thank you to all 3 of these. Thank you also to the people who assisted with our demo for, remember, dangling? There's the problem, the dereference, and then the undefined behavior. And thank you to Matthias and Gabor. Let's give them all a hand. And you can see their talk later today. So remember this checklist when proposing a new C++ feature, what are the things we should ask? Well, I hope that the lifetime profile addresses two of those things pretty directly. How does it simplify C++ code to make it easier to read, write, debug, maintain? Well, this analysis gets rid of a whole item in effective STL, and it gets rid of classes of errors that if we just could assume that people had on by default in their compilers as warnings, we wouldn't need to teach or document. We would at most need to teach what you write instead when it's not obvious. And by removing gotchas, special cases, classes of errors, even though it's not trying to get all dangling errors, but common classes of errors that we get over and over again in articles, talks, at this conference, in code, and standards committee mailings, and just diagnose them, we'll have so much more time to talk about better stuff and move the language forward and to deliver solid code. So for the rest of this talk, let's talk about metaclasses. And this is a different kind of simplification. We're going to switch gears and talk about simplifying class authoring. And I first introduced that last year. I talked about it here at CppCon. And I want to thank Andrew Sutton. Andrew, are you around? Please stand up and wave. Who did the implementation in Clang together with Jennifer and Wyatt. I'd like to thank Jennifer and Wyatt, too. They're not in the room today, but we thank them very much. Also, is Matt Godbolt in the room? Where are you, Matt? Here. Matt, don't we, keep standing, don't we all want to thank Matt Godbolt? And in particular, for hosting this implementation for us at cppx.godbolt.org, the metaclasses implementation for the past year plus. So thank you. So one of our goals over the past year, this is a progress report, this is a long lead item, it's still an experiment and effort that could fail. I sure hope it doesn't because I see a lot of promise, and here's the progress so far. It has gotten into SG7 for several reviews in the committee, in the study group SG7 on compile-time programming and reflection and generation. And I'll show you the feedback on the next slide. It was largely syntactic, but it helped us think about what we were doing better. But the structure is still the same. And the prototype now handles more of the examples. Last year it handled about 4 of the examples in the paper. Now it handles more, and I'll show a few. But first, in a nutshell, remember the idea is the C++ class, this big apple, already is flexible enough to express iterators, traits, properties, flag enums, base classes, values, irregular types, variants. And they're all expressed with this wonderfully powerful class concept that is so powerful and flexible it can express all that. The trouble is, because we can't give a name to a subset of that universe of classes, we can't give a name to an iterator. Concepts help. It helps us detect them. It doesn't help us author them. We don't get as much support for writing them, making sure we wrote them correctly, and so it tends to be brittle. There tends to be tedious boilerplate. We need to remember rules because the compiler doesn't enforce them. We need to write functions that aren't generated. The idea of metaclasses is that many language features, not all language features that we could imagine adding to C++, but the ones that are about kinds of classes, those future language features, I hope that we never need to standardize because I would like to be able to write them as libraries. That is the very high goal that we're going for here. And with no loss of usability, expressiveness, diagnostic quality, or performance compared even to other languages who wired them right into their language. And I gave some demos last year to support that. If you think that's a high bar, please watch the demos from last year. But I'm going to give you a quick update and then show you new examples. When you're writing a metaclass, the left-hand side was last year's syntax, the right-hand side is this year's syntax, and the main difference is in the wrapping. So the body is still the same, so the concept is still the same, the structure, but instead of the idea of, oh, I'm sort of mentally inside the class I'm writing and I'm reading my own definitions and modifying them, now the view is, no, I take a fully formed class, whatever the user wrote in source code as input, and I generate wherever I am things from that. And that could be I copy each item, it could be I do some validations. But the main thing is that you'll notice that at the bottom of the right-hand side that we might now explicitly generate things that were implicit before. I think this is an improvement, but the structure is still the same, but that's the new syntax to get used to. And it'll probably tweak again, but that was the committee syntax feedback, and I appreciated it. The other was when using a metaclass to define your own type. So on the left-hand side was last year, the right-hand side is this year. The committee really, really wanted to see the keyword class up front. And there are parsing benefits to that. We could still parse the other one, but there are definitely parsing benefits. And also by having interface in parens, you can have a comma list and have more things there. It becomes easier to express multiple metaclasses. But that's the change to applying a metaclass. So now let's see some examples. In each case, I'm going to show the example the way I teach it today. Every single one of these is examples I already teach, and you might have been in a course where I've taught it. So I will very quickly give you a condensed version of what it is we're trying to accomplish, how we do it today, and then we'll look at how metaclasses help us. Associating data with locks. How many of you have ever written a race condition? So we forget to take a lock, or we took a lock, but oh, it was the wrong one. Oopsie. That one passes code review more often. So here is the pattern, and I'm going to blow through this fairly quickly, but the main thing is to get the sense of what we're asking people to do. If we grouped the mutex at the bottom and the data it protects together in the same class or struct, now we could give instrumentation to figure out, oh, I now know that mutex goes with that data. I could do things like assert the mutex is held before I access the data, write an accessor around the data and assert the mutex is held. The middle three lines are boilerplate because they follow the locking the concept or the mutex concept in the standard library, just like the container concept is you have begin, end, value type. The mutex concept is you have lock, try lock, unlock. So we write those too, just so that the user can then take a MyData object and do a lock guard on it directly. So this works fine. But man, that's a lot of boilerplate to write by hand. Now, if I was going to automate this, the first thing I need to do, notice I assert the mutex is held. Turns out the standard mutex doesn't have that function. So we can wrap. If we want to make a mutex testable, basically what you do is you put a mutex and a thread ID together, and then you can provide your lock, try, lock, unlock. Every time you lock, you record the thread that held it. And when you unlock, you reset it to the default. And then you can say is held. So this is a helper I'm going to use. It's a little wrapper you write if your mutex doesn't already have an is held function. And then I always have to apologize for the next slide. I apologize for very few things in C++ because I love this language. But what's the thing we always have to apologize for? Starts with M. Macros. So I always start with, sorry for the macros, but. And yes, there are ways you could write this in a different way that could avoid the macros, but I don't believe you can write it conveniently without macros because in this way, because I want to write the code at bottom. I want to write, here's my struct my data. It's guarded with mutex type. It has a guarded member vector int, a type vector int named v, and so forth. And in that guarded member, I have to refer to, first of all, I have to use token pasting to make a different member name for the private member than for the accessor. Otherwise, I got to have the user at the bottom specify two names, just so that one is the public name and one's the private name, which is icky. But also, inside the macro, I have to then refer to the mutex that I declared earlier. So this is what we do today. It's what I've been teaching. After the class, half the time, somebody comes up and says, here's how I think you could write this without the macro, but it's a different design. That's also a decent design, but it's not this one. I really would like not to write the macro. But let me motivate why it's still worth it today. And by the way, we're never likely to standardize a special purpose language feature here in the standard. So this is today's status quo. Here's why it's good. Now imagine I have a MyData object, two of them, data1, data2. When I call data1.v, .pushback, as soon as I call data1.v, what's the very first thing that happens in the body of that accessor function? Assert mutex is held. Here I didn't lock it, so I'm getting a green line because it will fail. That's green because failure is good. That's exactly what I wanted. At test time, the first time I ever exercise that line of code in a unit test, I will get an assertion. That is way better than a random, hard-to-reproduce bug report from a customer site. Very first time I go through that first green line at test time, I will get the assertion. Same thing on data2.w. First thing it does is that mutex held? Data2's mutex, answer is no, I assert. Great, I just caught 2 race conditions. So let's say I comment those lines out and I go into the block and now I have that nice yellow lock guard line. Notice I'm using a lock guard on my data because it has lock, try lock, unlock. Now I say data1.v, very first thing it does is data1's mutex held? The answer is true, off we go. And the pushback is perfectly fine. Then I say data2w, the very first thing it asks is data2's mutex held? Now I have taken a lock, but not on that mutex. That assertion will correctly fire, and again, that green line will get an assertion deterministically at test time, the first time I exercise that code. And I cannot say how much better that is than a timing-dependent race. The one thing you shouldn't do is take that sneaky pointer while you've got the lock, access it, store a pointer to it, release the lock, and then use the pointer. I can't detect that. Fire that person. But I can detect Murphy. Maybe not Machiavelli, but I can detect Murphy. So this is a valuable idiom, but it makes me cry because it's so valuable. I teach macros even though I need macros. I show it even though I need macros to teach it, which is embarrassing. So on the left-hand side is what we write either by hand or at the bottom with macros. With the MetaClasses proposal, you can wrap all this up, and there's a live Godbolt example that I'm going to post in the paper when it gets updated for the next mailing. And I'll also show these examples on my blog over the coming few weeks and months. But I'll show you the code today. It's a class. It's guarded with mutex type. And I just say what the members are. I use natural syntax, not like the macros, which are macros, plus they don't let us use natural syntax. And I just generate what's on the left-hand side. I can directly express intent, and that makes their code simpler because they can utter a word of power. And we've enabled them with metaclasses to write the word of power guarded. By the way, did you notice this is a templatized metaclass? Let's see. So today, a metaclass is defined as template type T, T source. But here there's an additional template parameter, M, which is the mutex type. So what I'm going to do, and I'm showing part of the code, there's a couple of other context for functions it calls that do similar things up above, and you'll see that in the online example. I first call line 51 guarded with M, and what that does is it generates lock, try lock, unlock, and the mutex of type M. Then for every member variable, I do a guarded member of its type and its name. That is not a macro anymore. Rather, guarded member creates an accessor and a private variable with a suffixed name, which I can do without macros now with generation. And I create one of those for every member. That creates the accessors, and you see them on the right-hand side, where I create the accessor for V and for W and the private members. And I even have a compiler diagnostic, which at compile time, if somebody tries to make a guarded class that has no data members, I can give them a high-quality diagnostic. Because why did you guard something that's empty? And then I use it in line 70 at the bottom. All I write is class guarded std mutex. The same code I just showed you compiles to that today. This works. And I didn't need a language feature to do it. Reflection and generation is powerful. What's even more powerful is with the metaclass being able to give a name to a bundle of those things and reuse them. And so here's what we use. So I would say if you hate macros, you have a good reason to love metaclasses, and I hope you do. And if we're serious about whether people happen to like metaclasses immediately today or not, if you're serious about getting rid of the remaining reasonable use of macros, and I am, then you're going to love modules, you're going to love constexpr, and you're going to love reflection and generation at least. I happen to think that you will already, if not soon, also love metaclasses to be able to do this kind of thing, because now I don't need to teach that macro anymore if we have a standard way of doing this. And you might have noticed that today when we talk about patterns, we talk about cookbooks that you apply by hand. People have long said, yeah, patterns, you can't make those to be libraries. Oh, yes, you can. Let's talk about another pattern and make it a library. Active objects. First, let me give you the motivation, how we teach it today. Threads are our low-level way of doing concurrency. It's the only way in the standard really right now. But threads are too low level. There are no guardrails. They can do just anything in their execution. And their communication is with shared state by default. And that's just terrible. So we teach, discipline your threads. When you write a thread, this isn't for every use case, but it's for the vast majority of them. Write your thread mainline as a message pump that just accepts asynchronous messages and does them one at a time, which means it needs no other synchronization on its internal shared state because it's only executing one message at a time. And then communicate by sending it async messages and make them well formatted. Hint, we'd love to use the type systems such as, say, a function signature. That's statically a well-formatted message. A member function signature is a statically well-formatted type-safe message. And there are various options here. I'm just going to show a very basic option. You could do this with coroutines. You could use a series of tasks on a thread pool. You can use a priority queue, multiple channels. I'm just going to show an actual thread with one queue. And I'm pretty sure that most people here seeing that can then write the advanced examples pretty quickly by ourselves. But let's see how to do the basic example. And understand that in C++ we were never going to standardize something as narrow as an active async class. I don't see that ever happening. Like somebody proposes a class where every member function call is asynchronous and automatically returns a future. It's useful, but it's too narrow a feature. This isn't the language we would do that in. We like general features. So we encapsulate a thread in the message queue. We want to write code like this, where we have a class worker that's coded specially somehow, and when in the bottom that we invoke it, a function, we actually get a future, and then we can do other work concurrently while we wait on it. So every member function call is asynchronous and returns immediately. We want to directly express all these different kinds of things, long-running workers like a GUI thread, decoupled independent work like we'll see pipeline stages in a moment. So here's the key thing we want to do. We want to attach thread lifetime to object lifetime, because C++ knows all about object lifetimes. The way we do it is we teach it the way C++ knows it, which is hook the constructor and the destructor. So the constructor starts the thread and the message pump. The destructor sends a done signal and then waits for the queue to drain and then joins. You'll see in a moment how that directly lets us express object lifetimes in a clean way in real code. But here's a starter example. Once I've done that, I can have a nested class inside. So two active classes, one nested inside the other. And then when I instantiate the outer one and when I destroy it, I naturally, by construction, wait for the inner one to destroy first because I automatically destroy it. The language gives me that, thank you, Bjarne. It sends the done message for the internal active thread 2, waits for it to drain its queue, then returns, and then I do the destructor for the enclosing object, which sends the done signal for it. And so I've expressed nested concurrency really simply using existing concepts in the language, and this is really powerful. So how do I write this pattern or make it easy for people to write it? Here's a helper class. So a message is just a function that takes and returns void, just something executable. My constructor starts the message queue, and it starts the message pump. While not done, mq receive paren, get the next message, and then notice paren, immediately invoke it. There's two sets of parens there. That's not a typo. And that's it. That's the message pump. The destructor sends done equals true as a message So when that message is executed on that thread, it says done equals true, and then on its next trip through the loop, it says, oh, look, done is true, and exits. So we're sending the message that will cause the thread, the worker thread, the message pump to finish in order once it's drained all previous messages first. Then we just join and wait for that to happen. And send is just a wrapper for enqueuing a message. So that's the basic model. Now let's say we use that to, on the right-hand side, write a logger class that's thread safe. It's safe to call externally without external synchronization. Whereas on the left-hand side, the old way we would do it would be with a mutex. And we take a lock inside every call to the printline function. So the calling code is identical. The calling code is mylog.println hello %1 name. What's the difference between those two? Just shout out any differences that you see in how they work. Left one's synchronous, yes. So what's the right one? Asynchronous. Which is more scalable? Right-hand one. Why? Well, because on the right-hand one, does the caller ever block? No, caller never blocks. Now what are we doing? We're trading off space for time. We're going to queue up messages, so we're going to use space in order to get that concurrency, but the right-hand side is non-blocking. And so it'll scale better. And the left-hand side works fine, but it also does all the work on the caller's thread. The other nice thing about the right-hand side is all the work is done inside the active object worker thread. So not only is the caller not blocked, they're also pushing more work off their thread, because the actual formatting in the right-hand side is done on the worker thread. And so then you need to load balance this and make sure you're doing the right thing for throttling and everything. But in general, there's a lot to like about the right-hand side. And we can write this today. And notice the pattern. You make active your last member, and then you write every member function. You wrap its body in an a.send lambda. That's what we teach people today as the convenient way to write this. Now let's say that we have a typical pipeline. So here's an example I give a class, and basically what they have to do is they have to create a decorate thread, a compress thread, and an encrypt thread. The decorator decorates a buffer, puts it in a queue for the compressor, which takes it, compresses it, and so forth. So it's 3 pipeline stages, each a thread connected by queues. And so people take about a half an hour and they come up with a solution, maybe 20 minutes. Then I say, now write it generically using active objects, and then I show them this answer. You just write a stage. So here's the generic stage. It's just going to take a function, some function that takes a buffer star and does something with it. I don't know what it does, just something that can take a buffer star and stores it. Then it has a process function, which notice follows this asynchronous pattern, and this is the message. It's an asynchronous message that does whatever that work is on this buffer. And then the private state is just, it stored its buffer, it stored its work function it's supposed to do, and an active object at the end. Remember to put that one last. If you don't put it last, then the active thread's main line starts before the function is constructed. That you really, really want to put that active object last. Always remember that with this pattern by hand. As soon as I have this, I construct it with a piece of work to do. I have an async process message that just does it asynchronously and pumps the process message for everything, every buffer pointer that it's given. Now I can write the whole solution in a few lines like this. It's very clean. I create a stage named encryptor, and I give it a process function which simply says, for any buffer you're given, just encrypt it. That's it. I'm done. Pretty much no boilerplate there. That's pretty much the exact statement of what the encryptor does. The compressor takes a buffer pointer, it compresses it, and then sends it to the encryptor, which it captured by reference. And that's fine because these are nested lifetimes. There's no dangling possible here. And notice, by construction, I had to construct the objects in the right order. I had to create the encryptor first because the compressor refers to it. I can't write the code the wrong way because the compressor refers to the encryptor. So of course I write it first. Then I do the same with the decorator. The decorator is a stage which for each buffer, decorates it, and hands it to the compressor. And then I simply call the decorator and send it the process message to fill up its queue. And I've got this 3-stage pipeline that runs. And the cool part is, at the end, what do I destroy first? Decorator. What does the destructor of decorator do? It sends, it enqueues a done message for the decorator, waits for the queue to drain. So any decorations it was doing, it waits for it to finish. Then it sees the done message, joins and returns, decorator's done. Then it destroys compressor. Same thing, sends it the done message, waits for the queue to drain. We're draining the pipeline in the right order, naturally, because reverse order of construction is what Bjarne saw was the right thing and has given us for 39 years. Thank you, Bjarne. And then we join, and then we destroy the encryptor. We send it the done message, wait for its queue to drain, join, and return. And I have managed 3 worker thread lifetimes. I've done orderly setup and teardown. I could not write it the wrong way to get it in the wrong order. Everything is clear by default. I love C++. If you wrote this in Java, you can do it, but you are likely going to write the bug at the bottom because you still have to set up the stages in order because the encryptor has to refer to, the compressor has to refer to the encryptor. But you typically copy code and then destroy them in the same order, which is wrong. You have to destroy them in the opposite order. Java fixed this in 2014 with the try with resources statement, which lets you approximate what C++ does with nested local lifetimes. But just compare what we write in C++. This is just so clean. And I've managed 3 thread lifetimes and set up a multi-stage queue and drained it cleanly. And I can easily add flexibility. What if I want to add another end stage archiver, and the compressor sends some things to the encryptor, some things to the archiver? It's easy. It's like 3 more lines of code. Very general, very clean, and correct by construction. The only glitch is that today I have to write it by hand. With an active metaclass, I can just say class active stage, and I can automatically make every non-constructor, non-destructor be an asynchronous function. Now, for process, it returns void, so it's actually pretty easy, but at least I already see a benefit here where I don't have to declare the active member. I don't have to remember to declare it last. I don't have to wrap every body in a member function. And with the logger, same thing. We saw the logging example. I can write that as an active class. But how do I do this? Well, let's walk through it briefly. Async says, first of all, echo all the data members. For every data member there is, generate it, because whatever the user wrote, that's their data. Then for every member function, remember its return type. If it's not a constructor and it's not a destructor, we're going to want to make it asynchronous, because constructors and destructors are still synchronous. So first thing we do is we make the one that the user wrote private. Then we generate a wrapper that, notice at the bottom, it creates a promise, extracts a future, and calls the original, and does all that for you. And then we generate the actual function itself. And then I can write at the bottom class async test, and there's my one function h, and if we go back up, you'll see all the stuff that was generated, including the wrapper that takes the promise. And this also illustrates, and that's the whole code so far, and that also illustrates how hard this is by hand, because what I usually don't teach right up front in the talk, when I teach this, the active object method today, I do teach it, but I leave it at the end saying, yeah, and then what if you have to return a value? Oh yeah, okay. Let's talk about promises and futures and how to use stood promise, and here's how you do it. And so you actually have to write all of the stuff on the left today for this pattern if you want to actually return something. With the metaclass I just showed you, you write class active, and I'll just take that, and that double get result just automatically returns a future. And anybody who calls it auto whatever equals get result gets a future. It's just much cleaner and correct by construction, haha. And by the way, we've been talking about this member data of active types. That's really thread local storage, except with none of the overhead. It's by construction thread local, but it's just normal allocation. I kind of like that. Yeah, joining threads for the win, thread local storage by construction for the win, don't need special language features. Finally, property. How many of you use properties in C++? Yeah, a few hands. even though they're not standard, you are likely using a compiler that supports them. It's been invented many times in Qt, in Microsoft, Borland, even in Clang, because it has a Microsoft mode, and it also has support for other languages inside Clang that do have properties. And they're useful in practice and generally liked. But every time they've been proposed for standardization, they've failed because it's a narrow language feature. And the reality is this committee is just never going to standardize property as a language feature. There's just too much debate about, is it desirable? Our language is already big enough. Do we really need that language feature? Does it carry its weight? Which are reasonable things to ask. The reality is we're just never going to get it in the language. But what if we could write class-like language features as libraries if we have generation and metaclasses? Well, today in C#, I can write this. Pardon for the C#, but it's just an example of another language with properties. This is sort of a default version of a property where if you just write get and set forward declared, it generates a data member of that type and a trivial get return that member, set that member accessors for you because it's so common. And you can, with the implementation I'm about to show you, write this today. I'm very close to that syntax. I have to put one extra word in, but I think I can get rid of that next week. Thank you, Andrew. You can write class property of string, empty braces, so I want all the defaults, and I want to call it name. I'll show you how that works in a moment. But if in C# you want to, or in Qt, you want to have a non-trivial property, you want to actually say what your data type is, because maybe it's a compound data type, and you want to write your own get and set function, you can still do that. We just won't generate the defaults for you if you actually wrote them. So that's the model that we want to achieve. Here's how we do it. So the property metaclass, the very first thing it does is we're going to say, OK, I need to remember whether there's a value member, because I'm going to use that later. First thing in my for loop, I'm going to go through all of the member variables here, and I'm going to say, is their name value? If it is, I'll set has value equals true. And then I'm going to generate that. So I'm going to echo whatever the data members are, because there might be more than one if they wrote their own data members. Then for every member function, I'm going to say, was it get or was it set? Just because I'm now going to use that to give you them if you didn't write them yourself. So I'll remember that. But mostly I'm just going to generate that myself. And so I'm going to echo the functions that you wrote if you wrote them. Now, in the case, if there are no data members and there's no get function, then I'm going to generate a value of that type. So this handles the empty property case. But this is just compile time code, right? With reflection and generation, I can write this. If I reflect and I see there's no value, I will generate a value. And I'll remember has value equals true. So far, I have echoed any functions and data they've got. I've generated a value member if there wasn't one. Now I'm going to say, if there's no get function, every property has to have a get function, right? Const properties need it. Non-const may not have it, but const need it. Otherwise, why have the property? Now I'm going to say, if there is a value member, either generated or the one that I just created or the one the user wrote, I'm going to now generate my get accessor. If the user didn't write one themselves, this is the trivial one they get. And I'm also going to give a nice high-quality compiler error if they didn't write a default member, a value member. They wrote something else and expected us to write the getter. You can't do that. You have to either give us a value or write your getter. You can't leave both to us. We'll do both. Well, we'll do both of them, but you can't just have some members but not a value and expect us to know how to write the getter. So that gives us a nice high-quality error right there. Now, what about the setter? Not every property is writable. Well, in C++ we have const. And we have, in C++ already, std is const. So I'll just use that here. Std is const v because I like C++ 17 and I hate writing : value. So if t is const, and we don't already have a setter, and we have a value member named value, then I'll generate a set function, and just because I can, I'll overload it on constref and refref so to be maximally efficient for our values. because you're not going to see this code anyway. Let's do the efficient thing. It's only one more line. Then, finally, I provide a conversion operator that returns the value of this type, and then I'm going to generate the ways to set this value. Because what I'm going to do is I've created this class, and I'm just going to make one value of this class. That's it. Link-time codegen is really good at link-time optimization, and combat folding is really good at removing duplicates. So I'm just going to generate a class for this property and instantiate one variable for all time from it. And these are how you construct and access it. And then finally, today I have to write this and this. This code works today. I really would like to write this, but I'm so close to it already, I can smell it. And I know this one's going to be going away soon. And the committee wants class brackets, so OK, we'll give them a class bracket. That's close enough for me. But that works today, and I'll be blogging about it in the next few weeks with a live example you can try. So the goal of metaclasses is to expand the abstraction vocabulary we have in C++. And beyond just the built-in metaclasses, you might say, of class, struct, union, enum, we can generate defaults, enforce requirements on classes, and give a name as a word of power to this group of behavior, this kind of class that has these characteristics out of the universe of classes, and get rid of lots of side compilers, I hope, such as CuteMock, COM-IDLE, C++CX, which I designed, and part of my goal here is so I never have to design that again. Because I want to write it in C++. We did C++ CLI and CX because we couldn't write the information in C++. There wasn't enough there. I believe this gets us the rest of the way so I can write it in a potentially future, if this goes well, standard C++ somewhere down the road. If we can do this, then you would not have to wait for the standards committee to agree to add property to the language. You could write it as a short library and share it. You could actually do it. We could add it to the standard library. That's way easier than plumbing it through the language, which would take man-centuries of work, probably. And who has time for person-centuries of work per language feature? The benefits for standardization is if we can get more work into short, clear libraries, which are testable, than as language features, which have to be wired into a language specification and aren't testable easily. You have to pay somebody a lot of money to write test cases. I like code. Code is great. Code is testable, and being able to write that feature property as code that I can test is just a wonderful thing for me. So here's the checklist of things I said earlier. I think it hits all of them. It doesn't quite let us remove help exceptions in RTTI, but it does pretty much all the others, including the last, because as I showed with the guarded case, metaclasses and generation remove some of the reasons we need macros today. This is a direct step on putting the nail in the coffin of macros in new code by systematically, in this and with other features, removing the reasons that remain to write them. So we talked about more powerful and simpler, we talked about lifetime, and we talked about metaclasses. And it's time for XKCD. Randall wrote it, I didn't. The reason I mention this is because how many of you noticed that the lifetime rules compiler and the metaclasses compiler were both in cppxgodbolt.com? Oh, only a few of you noticed that. Let's have a couple of slides of fun. Here is one more simple metaclass, a metaclass called pointer. And it's just a toy metaclass, but it still does something useful. Every time you write a pointer-like type, whether it's an observer pointer or an iterator, what do we have to teach people? Oh yeah, overload operator star and operator arrow and make them do the same thing. Well, here's a little metaclass where you just write operator star. We make sure you wrote it, so you can't make the mistake of forgetting it. And we just generate operator arrow for you. So what it does is we're going to say, we're going to echo all the variables that it might have. We're going to just check whether it has an operator star. If it doesn't, we're going to complain. And then we're going to generate operator arrow that returns address of star, star this, just calls the star operator. And once we do that, we can simply write our own pointer type, We write only operator star, and if we forget, we get an error, and we get operator arrow for free. Okay, so there's a cute little toy metaclass, but this still does something useful. And here's what it generates. I wrote my data members, my constructor, those get echoed. I wrote my operator star, that gets validated. And then I generate the arrow operator, and everything is fine. And then when I use it, I can create one that's default constructed, and I can dereference it. And you might have noticed it has a squiggle. What do you suppose that squiggle means? If I take away the blackout, you will see the first part of the compiler output is the generation of the pointer class using the meta class. And the second then says, you're using that pointer type, and you're doing a null deref, set it to something before you dereference it. And I have one piece of code, and I get both of those together. I like features that work well together. And this is an example of how these simplifications add up and combine well. So let's try to pursue C++ evolution that makes user code simpler through abstraction, removes special cases and sharp edges, and lets us start to get rid of things, to deprecate or at least discourage older features that are less good, like macros. And lifetime targets that I've talked about targets the lower left, metaclasses target the other two. And hopefully these are ways that with these and other features, we can continue making C++ a simpler language for us all in the coming years. And I think that would just be great for the industry, for all of us, and for everyone. And we'd have a lot more fun in the language, too, that we already enjoy so much. We have time for just a couple of questions. If you'd like to come up to a mic, I'll take one or two, and then be happy to talk with you down at the bottom. Yes?
Hi, thank you. This metaclasses seems to be a really powerful feature, but how is it supposed to debug and test them?
Excellent question. How do you debug and test them? So I talked about that last year, so definitely watch the longer answer in that video. This is one of the reasons I show that compiler.debug, the reflect on the metaclass, so you can see what's outputted. That is the kind of information that what is generated that tools would expose so that you would be able to step into and do things like that and see what you're generating. But it lets us write that a lot more cleanly. Is there somebody at this mic? Okay, the next one here.
So in the new syntax for metaclasses, you're accepting a source parameter, which from all the code examples you've shown appears to be non-mutable. How do you control where you're generating to? In some of the examples, I'm guessing you're generating internal structs and things, but can you generate outside the class, and how do you control where that goes?
So currently, generation is where you are in place. So as you're defining class active, say, you're in that scope. You're defining the contents of that class. One of the things that we're extending is being able to write non-member functions. So today you can write member functions, you can write static member functions, and free functions that are declared in the class. And we're also providing ways to be able to declare things in enclosing namespaces and places like that. So that's coming. I don't have any examples that compile yet, but that will be coming in the coming months.
Right, thank you.
Yeah. Oh, yes, please.
So how would this mesh with, say, concepts? Can you say, like, oh, I have my pointer metaclass, I would expect this algorithm to have the concept is a pointer metaclass? So
one way to think about it, and I'm using Bjarne's words here, Bjarne...
Pointer is probably a bad example.
But that's okay, iterator, anything like that. So metaclasses are for constructing, for defining new types. Concepts are for querying them, so they're read-only. Now, every metaclass also comes with .is, so you can say whether it matches, just like a concept. So think of them as constructive concepts. That's the term Bjarne came up with, and I think it's apropos, because you're not just reading something, you're defining it to be this kind of thing, so you get generated defaults and things like that. The one thing that concepts does that this doesn't, and that's useful, and we could add the feature, or we can just use concepts here, is concepts. Whereas here you iterate through the member functions and say, oh, does it have foo? Does it have bar? Concepts, you can say, is foo of X a valid expression? You can do a use case-based query. And that's still useful. So I think these are very complementary features. You'll find some examples in the paper that use concepts in the implementations of metaclasses to query, oh, is this type assignable? If it's not, I'll generate something. But it's just it can just check for assignment or equality comparison using concepts use case style syntax and then generate using the syntax you saw. So I think they go well together.
Thanks. This is a very interesting feature.
Thank you.
I'm very excited by the lifetime checking features, and I'm curious to know that if you have sufficient annotation, is it possible that we can say mathematically that all dangling dereferences will be caught? And if so, what was the motivation for keeping this in tooling rather than as part of the language itself?
Well, so there's a couple of questions there. So first of all, this is designed to be implemented in a compiler. The Clang implementation is in a compiler. So it runs at compile time. It's a compile time diagnostic. So that's the kind of thing that can be in the language if we wanted to standardize something like that. So it can totally do that. As for whole program guarantees, it's possible that we could approach those or even get them. I'm a big fan of the 80-20 rule. I'm a big fan of the dangling problems I see in C++ are not because it's not formally type safe and memory safe. It's because I have regular patterns that people trip over all the time. And I can get those. Then we can see, well, how much is the other 20% or 2% more likely worth? It's worth noting that to get a formal guarantee of anything, like it's a cost benefit. We're taking a cost, like a design time cost, possibly runtime instrumentation, to get a guarantee. How valuable is that guarantee compared to the cost? So for example, type-safe languages like Java and C# aren't type-safe. That's heresy, but it depends on your definition of type safety. They implement the type safety they specify. They don't detect use after dispose, for example. They have resurrection instead and get to teach that. So it all depends on how you define it. I believe you can get a very practical level of leak freedom and dangle freedom, rather, and by being able to handle many common cases that we already know are real cases because we've been teaching people about them for 10, 20 years. So I'm optimistic that we will be able to handle the important ones. Then we'll see if we get to any whole program guarantees. Yeah, one more, please.
So at the beginning of the talk, you talked about features in the language that basically have been completely overtaken by newer features, so are there for compatibility. Like OpenGL expresses a core versus compatibility profile. What are your quick thoughts on expressing the standard in such a way?
That is exactly what I had in mind and tried to recommend we start thinking about in the first part of this talk. I think we are already effectively doing that in practice. In particular, the whole reason Bjarne created the core guidelines, and Bjarne and I created the core guidelines, was to be able to create a set of rules where you don't do this in new code. That's for old code only. New code is, we set up guardrails and rules for, here's the subset of C++ that is recommended today, and that we can keep moving forward. So that is implicitly creating such a distinction. So we're already partway down that road. I am specifically including a call to action to start seriously thinking about a future someday where we actually have, here are compatibility mode features with a fence around them that we only need when we're in compatibility mode, and consider having a mode that is a subset that is new code only, that doesn't include that.
That all compilers would then agree on what that is.
Yeah, so that's, I'm certainly speaking only for myself. I'm not speaking for Bjarne, I'm not speaking for the standards committee. I'm just observing we're already doing some of this. I happen to think it's desirable to start thinking about, is it worth standardizing such a subset? We'll see where it goes. I think it's going to be some years off, but it's worth thinking about now in order to plan for then.
Very good.
Yeah. So thank you. Thank you all for coming. Enjoy your lunch and the rest of the conference.